Now in this lecture video, we're going to start looking at hypothesis tests about a population median. Let's start off by refreshing our memories as to the definition of a median. So let y be a random variable from a distribution with median, which we'll denote by cap m. By definition, a median cap m is any value, any real number, that satisfies the following two conditions. First, the probability that the random variable y is less than or equal to this value cap m is greater than or equal to 0.5, and the probability that the random variable y is greater than or equal to cap m is also greater than or equal to 0.5. Now, it may seem a little cumbersome, but the reason it's expressed this way is because the definition has to apply both to discrete distributions and to continuous distributions. And so that is why it's expressed this way. Now, if y is a continuous random variable, then these conditions can be stated in the following way. So we still have two conditions. The first is that the probability that y is less than or equal to cap m is equal to 0.5, and the probability that y is greater than cap m is also equal to 0.5. So if you notice, by virtue of the random variable being a continuous random variable, these inequalities in the previous slide, let me go back there, you can see here we had inequalities, but here they become equalities. So again, the definition simplifies somewhat when we have continuous random variables. Now, this is going to be important to keep in mind as we consider developing this test for a population median. So let's start off looking at a right-tailed test about a population median. You'll remember back to the various types of hypothesis tests that we've looked at before, and in every situation we had really three types of tests. We had a two-tailed test, a left-tailed test, and a right-tailed test. So when testing hypotheses about a population mean, we had a right-tailed test, a left-tailed test, and a two-tailed test. When we tested hypotheses about a population proportion, we had the same three types of tests. In fact, even when we tested hypotheses about a population variance, we had the same three types of tests. So it should come as no surprise that when thinking about developing hypothesis tests for a population median, that we would have these three kinds of tests, and we will. We're going to start off with a right-tailed test rather than a two-tailed test, just because I think it's a little bit easier to motivate the test in a one-tailed fashion. Okay, so let's look at the setup here. Let y1, y2, and so forth out to y sub n be a random sample from a population that has a median of cap m. And suppose that we wish to perform a hypothesis test of this form. So the null hypothesis is that the median of the population is less than or equal to some specified value, cap m sub 0, and the alternative is the logical complement of that, the opposite of that, that the population median is greater than this hypothesized value. And suppose that we want to perform this test at a significance level of alpha. Now, you'll remember that alpha, the significance level, is something that we choose, all right, and it represents the probability of a type 1 error. So in this case, alpha, whatever we choose to use for that value in a particular situation, represents the probability of rejecting the null hypothesis and concluding that the median of the population is greater than the specified value when in fact the null hypothesis is true. Right? And obviously, if the null hypothesis is true, we don't want to reject it, but we know that in any real-world hypothesis testing situation, that's always a possibility. The probability of that type of error is alpha. And so when we perform the test in an actual situation, we may choose alpha to be 0.05, a 5% chance of rejecting the null hypothesis when we shouldn't. Or we may choose it to be smaller. We may choose it to be 0.03 or 0.01. Right? Whatever makes sense in the context of a particular problem, as we were talking about in a previous lecture. Now, given what you've learned about hypothesis testing thus far in the prerequisite statistics class, how would you go about constructing a test to implement this? Okay, I want you to think about that for a second. We haven't developed the test yet, so thinking ahead, how would you go about doing that? You might want to stop the video for just a few minutes and just kind of ponder that, maybe sketch some things out. You know, how would you actually come up with this kind of a test? Now, we're going to define a new random variable based on a function or using a function, which I will denote by cap I. Okay, so this function cap I is called the indicator function, all right? And the argument, the object that we feed or at which we evaluate this indicator function is a statement that is either true or false. And so it could be a statement, it could be a relationship, any kind of a statement that is either true or false. And the indicator function is going to be defined so that it's equal to 1 if the statement in the parentheses is true, and 0 if the statement is false. Okay, so then what we're going to do is we're going to use the indicator function to define a new random variable based on the random variable y. So again, and let me go back to the previous slide, the y's constitute this random sample from a population with median cap m. And so we're going to be defining a new random variable, which I will denote by x sub I, based on y sub I for each of the i's going from 1 to n. So based on y1, I'll define a new random variable x1. And then based on y2, I'll define a new random variable x2 and so forth. And so I'm going to define this new random variable x in terms of the random variable y using this indicator function. And the statement inside parentheses, the condition that I want to check, is whether the ith observation y is greater than the hypothesized value of the median cap m0. And so if y sub I is greater than cap m sub 0, then x sub I is going to be equal to 1, as we've indicated here. And if y sub I is less than or equal to cap m sub 0, then x sub I is going to be equal to 0. And so that's how we're defining this new random variable x in terms of y. Then what we're going to do is we're going to add up the x sub i's. All right, and we're going to call that the sum of those x sub i's by x sub tote. So x tote is the sum of the x's, and what that represents is the number of the y's that are strictly greater than the hypothesized value cap m sub 0. And so what we're doing here, as you can see in the title of the slide, for this hypothesis test, we are coming up with a test statistic. As you'll remember, as we talked about in the last lecture video, there are several things we need, and one of them is a test statistic. And that test statistic has to behave differently under the alternative hypothesis than it does under the null hypothesis. And so the first thing we need to do is come up with a candidate test statistic. And the candidate test statistic that we're looking at here, or developing so that we can look at it, is the number of observations in the sample that exceed the hypothesized value of the population median. Now, because the y's constitute a random sample, they are independent and identically distributed. And so because of that, the probability that the ith y is greater than m sub 0 is the same for each I. And so let's denote this common probability by lowercase p. So lowercase p represents the probability that y sub I is greater than the hypothesized value of the population median cap m sub 0. Now, again, because the y's constitute a random sample, not only are they identically distributed, but they are stochastically independent. And because of that, the events y sub I being greater than cap m sub 0 are independent as well. And so that means that the x's that we've defined are independent. The random variable x tote is counting the number of y sub i's that are greater than cap m sub 0, the hypothesized value of the median. And so the way we can think about this is that we have a sequence of n trials. Every y sub I that we get constitutes a trial, and then what we're going to do is we're going to dichotomize each of those trials. And the dichotomization that we're implying here, or implying, is whether or not the y sub I is greater than cap m sub 0. So there are two possibilities: either it's greater than or it's not. And we're going to define, we're going to call a success if y sub I is greater than cap m sub 0. So we have a sequence of n independent trials. Each trial is either a success or a failure. The probability of what we're calling a success, y being greater than cap m sub 0, is the same on each trial, and that common probability is p. And then finally, x tot is counting the number of successes that we have in our n trials. And so based on what you learned in your prerequisite stat course, you know that x tot has a binomial distribution with n trials and success probability p. And so we have found a potential test statistic to use, but in order to use it, we need to understand the sampling distribution of that test statistic. And we've identified the distribution of x tot. We know that it has a binomial distribution with n trials and success probability p. In particular, what we need to know is its behavior under the conditions of the null hypothesis. How does it behave under both, and does it exhibit different behavior? And if it does, then we can use it as a test statistic. But we need to specifically know how it behaves under the null hypothesis. And so let's take a look and see how this statistic behaves under the null and alternative hypotheses. Now, in this graph, we see two distributions, and for the sake of having a distribution to plot, I'm just using normal distributions. But let me just say up front that everything that we're doing here, it's in general. Nothing here depends on the distribution we're sampling from being a normal distribution. All right, I'm just using this for illustrative purposes, in large part because we're familiar with what the normal distribution looks like. But again, keep in mind that the development that we're doing here is going to apply regardless of the underlying distribution. So we've got two distributions. One of these distributions has a median equal to cap m sub 0. That's the green curve. And the red PDF has a median that is consistent with the alternative hypothesis that m is greater than m sub 0. Now, if the null hypothesis is true, right, and again, let me go back a few slides here just to refresh our memories. Let's make sure we understand what we're talking about. Okay, these are the hypotheses that we're testing. If the null hypothesis is true, and in particular, if the boundary condition of the null hypothesis is true. Well, now wait a minute, what does that mean? Well, the boundary condition, it would be here that cap m is equal to cap m sub 0. So if the boundary condition of the null hypothesis is true, so that the distribution we're sampling from is actually this green curve, then let me ask you, what is the probability of p? I'm sorry, not what is the value of p? Well, what is p? P, remember, is the probability that a randomly selected observation from this distribution is greater than cap m sub 0. So if the boundary condition is true, if the distribution that we're sampling from is actually this green curve, what is the probability that a y value that we get is greater than the median cap m sub 0? Well, clearly, you can tell by the graph that that probability is going to be 1/2, 0.5. And we could, if we need to, we could go back to the definition of a population median. And by the way, okay, I see I have a typo here. I didn't see that before. All right, but correct this in your notes. This should say definition of a population median. All right, I'm glad I went back to this slide. Okay, so I can fix that. Okay, but with that in mind, by virtue of the definition of the population median, the probability that y is greater than cap m is 0.5. So if the population median is in fact m sub 0, then this probability, little p, is 0.5. Now, what if the alternative is true? All right, what if cap m is greater than the hypothesized value cap m sub 0? So that we have a situation that looks like the red curve here. So if that's the case, what is the value of p, or at least what is the value of p in relation to 0.5? Well, if the distribution that we're sampling from is actually this red curve, then we can see that the probability of getting a y greater than cap m sub 0 is 0.5 plus whatever that area is. So we see that it's something greater than 0.5. So if the alternative is true, then that probability is greater than 0.5, and you would agree that the larger m is, the greater the value of p. Okay, so if the boundary condition of the null hypothesis is true, in other words, if cap m is equal to cap m sub 0, then x tote has a binomial distribution with n trials, and in particular with p equal to 0.5. On the other hand, if the alternative hypothesis is true, right, so that if the population median is greater than cap m sub 0, then x tote still has a binomial distribution, but p is greater than 0.5. Now, remember, the mean of a binomial distribution is equal to n times p. And so if the null hypothesis is true, then x tote has a binomial distribution with parameters n and p equal to 0.5. And so the expected value of x tote, or the mean of its distribution, is n over 2. If the alternative is true, then the expected value of x tote, the mean of the sampling distribution of our test statistic, is something greater than n over 2. And so from all this, if the alternative hypothesis is true, then the random variable x tote will tend to be larger than it is than when the null hypothesis is true. Does that make sense? Therefore, large values of x tote provide evidence against the null hypothesis and in favor of the alternative hypothesis. And so what we're seeing here is this differential behavior in the test statistic under the null hypothesis and under the alternative hypothesis. If the alternative hypothesis is true, then we'll tend to see larger values of x tote than we would if the null hypothesis were true. And so because x tote behaves differently under the null and alternative hypotheses, and we understand the difference in that behavior, then we can use x tote as a test statistic for performing this hypothesis test. Now, how do we come up with a decision criterion for deciding whether or not to reject the null hypothesis? Well, in order to come up with a critical point, or come up with decision criteria that we can use, we need to know how the test statistic behaves under the conditions of the null hypothesis, and in particular at the boundary condition. And so the next slide that I'm going to bring up shows the sampling distribution of x tote when the boundary condition of the null hypothesis is true. When the null hypothesis is true, we know that p is equal to 0.5. So x tote has a binomial distribution with a number of trials equal to whatever the sample size happens to be. In this particular graph, I'm using n equal to 10, but it could be anything, all right? More importantly, we know that p is equal to 0.5. Now, in our previous review lecture on the binomial distribution, one of the things that we learned was that for the binomial distribution, when p is equal to 0.5, that binomial distribution is perfectly symmetric. So that is why we have a symmetric distribution right here. This is a graph of the binomial distribution with n equal to 10 and p equal to 0.5. And because p is 0.5, the distribution is necessarily symmetric. Now, let me ask you this question. What values would we expect to see x tote take on if the boundary condition of the null hypothesis is true? In other words, if the population median cap m is equal to cap m sub 0. Well, when the boundary condition is true, this is the sampling distribution, this is the probability distribution of x tote. All right, and the areas of these rectangles give us the probabilities associated with x taking on the values from 0 up to 10. So would we expect x to take on the value 0 if the boundary condition were true? Well, probably not, because its probability is 0.001. Would we expect to see a value of 10 if the null hypothesis were true? Well, probably not, because the probability of that is 0.001. And this is really what we should be focusing on up here anyway, because this is a right-tailed test. So as we can see in the graph, the probability is 0.989, that x tote will take on a value less than or equal to 8 if the boundary condition of the null hypothesis is true, right? Because the probability of the values in the sample space less than or equal to 8, which would be the sum of these areas, and note that the areas are given above the rectangles. So if the boundary condition of the null hypothesis is true, then there is a very high probability, in fact a probability of almost 99%, that we'll see a value of x tot less than or equal to 8. There's only a 1.1% chance, a probability of 0.011, that we would see a value of x tot being equal to 9 or 10. And so I think you would agree that x tot taking on values 9 or 10 would be very unexpected if the null hypothesis is true. So now we're going to look at how to calculate the p-value for this test. We're going to use the fact that if the null hypothesis is true, then as we've said on a previous slide, x tot has a binomial distribution where p is equal to 0.5. For a given sample, let's denote the observed value of cap x tot by little x tot, lowercase x tot. Then the p-value for the test is given by the following conditional probability. And this should ring a bell, it should make sense, because this is how we would calculate p-values for other right-tail tests that we've looked at. All right, the p-value for this test is the probability of observing a value of cap x tot at least as big as that which has been observed if the boundary condition of the null hypothesis is true. And so to calculate this probability, we're going to add up the values of the PMF, the probability mass function, of this binomial distribution from little x tot up to n, and in evaluating the PMF, we are evaluating it at this condition where p is equal to 0.5. All right, so this is how we calculate the p-value. How do we use the p-value then in deciding whether or not to reject the null hypothesis? Well, we do what we always do. We reject the null hypothesis if the p-value for the test is less than or equal to alpha, where alpha is the significance level being used for the test. In our example that we looked at above, let me go back to it. Okay, this situation where we've got n equal to 10, all right, and if the boundary condition of the null hypothesis is true, then p is equal to 0.5. So this would be the sampling distribution of x tot under the conditions of the null hypothesis. Suppose that we observe a value x tot equal to 8. What's the p-value of the test? Well, the p-value would be the probability of observing a value of x tot equal to 8 or 9 or 10. So observing a value of x tot greater than or equal to 8. Well, all we need to do is add up these probabilities, 0.044, 0.01, and 0.001. And that is what we're doing here. We're calculating those probabilities. And we get a p-value of 0.0547. So that's how we would calculate the p-value. Now let's think about the CDF, the cumulative distribution function of the binomial distribution, and let's denote it by cap f. All right. So since we're denoting the PMF of the binomial distribution by lowercase f, we'll use cap f to denote the CDF. Remember that the CDF of a distribution is equal to the probability that the random variable is less than or equal to the value at which we are evaluating the CDF. So the CDF evaluated at little x is equal to the probability that cap x is less than or equal to little x. And so and actually what I ought to have right here is cap x tot. All right. So thinking about or utilizing the CDF here, we can re-express the p-value in terms of the CDF in this way. So the p-value is equal to 1 minus the CDF evaluated at little x tot minus 1 under the assumption that p is equal to 0.5 here. Now why do I bring that up? Well, it's because the TI-84 calculator has both the PMF and the CDF of the binomial distribution built in. So we can use that to calculate p-values very, very easily. So if you go to, on your if you have a TI-84 calculator, this is where you would find it. If you've got some other calculator that has these distributions, you'll have to see where they are. But on the TI-84, if you go to the second key and then distributions, DISTR, then you will get the distribution menu. And if you scroll down, then you will see the binomial, it says PDF, but it's really a PMF. So the binomial distribution PMF, option A, and then option B is the binomial CDF. So this gives us the functionality that we were talking about on the previous slide, right? It gives us this cumulative probability. So the image to the right shows a partial list of the distributions and their functions in the distribution menu on TI-84. And then the next slide shows the p-value calculation using the calculator when little n is equal to 10 and x totes equal to 8. So let me back up one slide for a second. We're going to show how to calculate the p-value using this formula here, using the binomial CDF. And so this is how we would do it. So we want to evaluate, want to find the p-value where x tote is equal to 8. Well, we've got to subtract 1 from 8, so we got 7 there. Right? We need to subtract this CDF from 1. So 1 minus the binomial CDF, where n is equal to, oh, and you can see here where I'm inputting the value. So I've got 10 trials, a success probability of 0.5, and then the x value at which we want to evaluate the CDF is little x tote minus 1, so 8 minus 1, or 7. And then when we paste that into the menu, all right, this is what we get. So notice what I had to do is 1 minus, and then I went into this menu and got the CDF, okay, input these values, and then it pasted in that function. And so when we calculate this, when we evaluate this, we get 0.0546,875, the same value that we got back here. All right. So this is a very nice, handy way to calculate p-values for this kind of a test. Okay, so let's look at an example. So the data in the table below are a random sample from a normal distribution with unknown mean and unknown variance. Since for a symmetric distribution like the normal, the median and the mean, if it exists, are equal, and so inferences about their common value can be made using procedures for means or procedures for medians. In this example, let's frame the question in terms of the population median and use the procedure that we've just discussed to answer the question. And the question is there sufficient evidence at the 0.0592 level of significance to conclude that the median of the distribution exceeds 100? Now, let me just say a few things before we continue on. Again, I'm using a normal distribution. I'm getting a random sample from a normal distribution, mainly for convenience sake, all right, for the purposes of generating the data. But the normality plays no part in this. We could do this for really any kind of a distribution, all right? But there are some additional reasons why I'm using a normal distribution that we'll see as we go on, but mainly for teaching purposes. But again, this procedure does not depend at all on the data being normally distributed. I just want to make sure that you understand that. The other thing is, it says here, for symmetric distributions, the median and the mean are equal, and that statement makes sense if the mean exists. I guess what I would just say here is that there are some symmetric distributions, and we'll probably see an example or two, where if you were to look at a graph of it, you'd say, well, certainly the mean exists, but in fact it does not exist. But the median does exist. So that's one of the reasons why it's important to know how to frame questions in terms of medians, because there are some strange distributions for which the mean does not exist. And then the last thing I'll say is the level of significance we're using is 0.0592. Well, that's kind of strange. Why not use 0.05 or something like that? Well, we'll see here in a minute. So is there sufficient evidence at the 0.0592 level of significance to conclude that the median of the distribution is greater than 100? And so we see our sample data here. We've got 15 observations, and we want to know whether there's sufficient evidence to conclude that the median of the distribution is greater than 100. So just take a look at those data. Just eyeball it here. What do you think? Do you think there's going to be significant or sufficient evidence? Okay, so here are the null and alternative hypotheses for the test. And notice that the alternative says the median is greater than 100. Now, that's what we're trying to show, and so it goes in the alternative hypothesis. All right, and then the opposite of that, the logical complement of that, would go in the null. So the null hypothesis is that cap m is less than or equal to 100. The rejection criteria for this test can be specified either in terms of a critical point or in terms of the p-value. right? And we're going to do both just for the sake of completeness and to show how to do it. To specify the rejection criteria in terms of a critical point, we would need to take a detailed look at the sampling distribution of the test statistic X tote, and in particular under the boundary conditions of the null hypothesis. And so under the boundary conditions of the null hypothesis, we know that our test statistic X tote has a binomial distribution, in this case with n equal to 15 and p equal to 0.5. And so the next slide shows the information we need about this sampling distribution in order to come up with the appropriate critical point. So what I've got here are 3 panels, and I'm showing here how to come up with this information on a TI-84 calculator. So the first thing I'm doing is generating the sample space for this binomial distribution. The sample space consists of the numbers, the integers from 0 to 15. Those are listed here in list L1. And notice I can only show 10 at a time, so I show 0 through 10, I'm sorry, 11 at a time. So I show 0 through 10 here, and then the rest down to 15 on the bottom panel. Okay, then in the second column, list 2, I've got values of the binomial PMF. And so these are the probabilities associated with each of the values in the sample space. In the third list, list 3, I've got values of the CDF, the accumulated probabilities. And then in the fourth column, L4, I've got 1 minus the CDF. So you can see here that, for example, 1 minus 0.1509 is 0.8491, and so forth. And so our hypotheses, the null hypothesis, cap m less than or equal to 100, the alternative cap m greater than 100, the rejection criteria, okay, in terms of the critical point, we're going to reject the null hypothesis if X tote is greater than 10, and I could also put if it's greater than or equal to 11. And now where do we get this? Why is this? I go back to the previous slide. From this bottom panel, we see that the probability that X is less than or equal to 10, or the probability that X tote is less than or equal to 10, is 0.9408. Now 1 minus that represents the probability that X is greater than 10, and that probability is 0.0592. And that is the significance level that we're wanting to use. Now the reason we're using this kind of a funky significance level of 0.0592 is because when we look in this column of values here in list 4, we don't see 0.05. Because the sampling distribution is discrete, we don't have every possible significance level available, at least in this column. I mean, we could still use a significance level of 0.05, but it's not going to show up here. So I just wanted to use a value in this list, in this example, as the significance level, and the one that's closest to 0.05 is 0.0592. All right, so that is where we come up with this rejection criteria. We're going to reject the null hypothesis if X tote is greater than 10. And using that as our rejection criteria, we see that the probability of committing a type 1 error, which is alpha, is 0.0592. Now, another way to specify the rejection criteria is to express it in terms of the p-value, which we know how to calculate now. And the way that we always use the p-value is that we reject the null hypothesis if the p-value is less than or equal to 0.0592, or less than or equal to alpha, less than or equal to alpha. And if we're using a significance level of 0.0592, then this is the rejection criterion for this test stated in terms of the p-value. What I've done here is I've replaced the actual y values by the x values. Remember, x is an indicator variable. It's 1 if the particular y value is greater than the hypothesized value, in this case 100, right? And 0 otherwise. And so we see that we've converted the y values into our x indicator variables. All right, and so it looks like we've got 12 values in the original sample space, all right, that exceed, 12 values in the original sample, the y values, 12 y values that exceed the hypothesized value of 100. So the test statistic X tote is equal to 12, and we know using the critical point method that since x total, which is 12, is greater than 0.1 or greater than 10, then we would reject the null hypothesis. We can also use the p-value method, and so we calculate the p-value. Right? The p-value is the probability that x total is greater than or equal to 12, the observed value, under the assumption that the boundary condition of the null hypothesis is true. In other words, that cap m is equal to 100. All right, and we see that that probability is 0.0176. Note that the probability that x total is greater than or equal to 12 is the same as the probability that x total is strictly greater than 11. And so if we go to this row here where we've got 11 in that first column, then that's where we get the 0.0176. So what's our conclusion? Since x total, which is 12, is in fact greater than 10, or equivalently, since the p-value is less than or equal to 0.0592, there is sufficient evidence at the alpha equal to 0.0592 level of significance to reject the null hypothesis and conclude that the alternative is true, which says that the median of the distribution is greater than 100. Now, note that based on the p-value, which is 0.0176, not only would we reject at the 0.0592 level, we would reject at the 0.05 level, we would reject at the 0.04 level, we would reject at the 0.03 level, at the 0.02 level, we would even reject at the significance level of 0.0176. However, we would not reject the null hypothesis at the 0.01 level, right? Because if we were using alpha equal to 0.01, the p-value is not less than or equal to that, and so for a 0.01 level test, we would fail to reject the null hypothesis. But for a 0.0592 level of significance or a 0.05 level, and for any level down to and including 0.0176, we would reject the null hypothesis and conclude that the median is something greater than 100.